Hi class. Today, I'll be introducing a model called BART. So what is BART actually? The BART stands for bidirectional and auto-regressive transformers. So it is bidirectional and it is auto-regressive. We'll dive into that in more detail. But before that, what can BART do? Actually, BART can be applied to a variety of NLP tasks, including extractive question answering and summarization, dialogue, and translation. For example, for extractive question answering, there's a task called squat. So the input for this task is a context paragraph, as well as a question sentence. And the output is the start and end index within the context paragraph, which will be the answer. BART can also do text summarizations. The input is a text, and the output is its summary. Related work. Actually, in the BART paper, it mentions several related works. I picked 3 of them, which I think are the most important. They are Transformer, BERT, and GPT. Let's start with Transformer. Transformer was introduced in 2017 in the famous paper Attention is All You Need. And since then, it became the overkill and the bedrock for the large language model. Transformer is actually a stack of encoders and decoder blocks. For encoder, the thing I want to mention is that it uses multi-headed self-attention. The self-attention is bidirectional, which means for a given position, it can look at information on its left as well as on its right. So this, and for the decoder, it uses mask self-attention. So the mask self-attention is unidirectional from left to right. After transformer, there's another famous model called BERT. BERT uses only transformer encoders. It is pre-trained with 2 tasks, masked language model and next sentence prediction. For masked language model, we sample some positions in the sentence and replace them with a mask token. And since BERT uses transformer encoders, it is bidirectional. It can interact with information on both sides, so it's good for comprehension. But BERT is not so good for generation tasks. There's another model called GPT, which only uses transformer decoder. As a result, it is auto-regressive, unidirectional, and good for generation tasks. Now, it's final time for BART. So let's first have an overview of BART's model architecture. BART uses standard transformer architecture, so it is sequence to sequence, but with some modification. Those modifications are, first, activation function, the way to initialize parameters. Also, BART does not have feed-forward neural network before word prediction, which is the neural network after the last decoder's output. So BART has 2 sizes. BART base contains 6 encoders and 6 decoders, and BART large have 12 layers each. For the pre-training of BART model, we then feed the corrupted document into the encoder, which is a bidirectional model. Then we predict with the decoder. We try to predict the original document. So BART is trained by optimizing a reconstruction loss, which is cross entropy loss between the decoder's output and the original document. So I think the most amazing things BART did is it used corrupted document during pre-training. So there are actually 5 types of ways on how to corrupt your document. So the first is token masking, where we sample random tokens and replace them with masked. So this is similar to what BERT did. And the second is token deletion, where we delete random tokens from the input. Text infilling. Instead of sample tokens, we sample a span of tokens from a Poisson distribution and replace this span with a single mask. Sentence permutation, where we shuffle sentences in a random order. And the last one is document rotation, where we chose a token randomly and rotate our document so that it begins with that token. After we had a pre-trained model, we can then fine-tune BART for a lot of downstream tasks. The tasks that BERT can be fine-tuned include sequence classification task, token classification task, and sequence generation task, and machine translation task. So for example, when we fine-tune BERT on sequence classification task, we use the same input to be fed into both the encoder and the decoder. And we will use the final hidden state of the final decoder and feed it into a linear classifier for multi-class classification. So this is similar to BERT. BERT use its CLS token at the last encoder layers, and for classification. Here for BART, we use the last hidden state of the final decoder layer. So another example is to fine-tuning BART on machine translation task. So for machine translation, we replace the BART's encoder embedding layer with a newly randomized initialized encoder. So we train this encoder as well as the model. We train them together, and the new encoder is expected to map foreign words into an input that BART can denoise into English. Experiment. So the paper have done 2 experiments, and the first one is comparing pre-training objectives. So what they did is it compared BART with some with other pre-trained models that are with similar size. So and these models are evaluated together on the following task: question answering, task classification, and generalization and summarization. And the experiment results are follows. So we'll explain it in detail. So from the experiment, so we have 3 observations. The first one is BART with text infilling performs the best. So the role when we test BART with text infilling is marked as red. We can see that it performs the best for 3 tasks, which are squad, exam, and conv AI2. So the second observation is performance vary considerably across tasks. So for example, pure language models seems to perform best on ELI5. So this corresponds to the 3rd column, which I mark red. So while bidirectional encoders are crucial for squad. So squad is a comprehension task. So those bidirectional encoders such as mass language model or BART with token or text encoding, since performs better than the unidirectional language model. Third, token mask is crucial. So as we can see, for BART model, we corrupt our document in many ways. And we can see from the result that if we only do document rotation or sentence shuffling, the result is not as good as if we do text infilling or token masking or token deletions. And the second experiment involves large-scale pre-training. What it did is it trained BERT large using the same scale as Roberta, so which is a BERT variant, and it compared this model with other models. So there are some details on the BART, on the large-scale BART. So it has 12 layers for encoder and decoder, hidden size 1022, and it is pre-trained on 160 gigabytes of data. So what this experiment looks like is that for discriminative task, this large-scale BART performs comparably to Roberta and XLNet. So like for some tasks, it outperform this model, and for the other tasks like squad, it is not good as good as Roberta, but it is very close. So that implies that BART's unidirectional decoder layer do not reduce performance on those discriminative tasks. And observation 2, for generation task, BART outperforms existing models on all of these tasks. So that is quite amazing. So that's it for the theoretical part. Let's move on to demos. First, I'll introduce you guys a website called Hugging Face. So this is where you can download the BART models. In Hugging Face, we first type in BART and we search for result. After that, we sort it by most downloads. And we can see that the 3 most popular BART model, they are all from Facebook. So one is BART large CNN, and the other one is BART large MNLI. So these are the 2 models that are fine-tuned on specific tasks. So and there's another one called BART base, so which is the based pre-trained model. And if you want to see more details, you can go to the docs. So I have opened the doc link. So on this link, you can there's overview and some implementation details and how you can use BART like for specific tasks, such as code generation, sequence classification, QA, and causal LM. All right, so next we'll do some code demos. So the first thing I want to demonstrate is a BART-based architecture. So we import the transformer model. This is already imported by Google Colab. So we just import the library, and we load the tokenizer as well as the BART model. So the model will be used is BART base. And then we print the model we just loaded. And the result would be like the architecture overview. So it might take some time. Okay, there we go. So as we can see, the BART base has an encoder-decoder architecture just as transformers. So it has 6 encoder layers from 0 to 5. Inside each encoder, we have a self-attention layer, a layer normalization, and then two fully connected layers. So this is like the same as transformer. Also, we have 6 decoder layers. Inside each decoder, we first have a mask self-attention, and then a layer normalization, and then a encoder-decoder cross-attention layer. And the last is fully connected layers. So that's the basic architecture for a BART model. So next will be experiment on using BART to do news summarization. So this is one type of generation task. So we load the model using BART for conditional generation. So this is also on the docs if you want to check it out. So after we load the model, we first input a task. So this is the news I chose from CNN. So this is the original news. So I just extract one paragraph, which is this paragraph. So that is our input. It says like the Justice Department's recommendation come after a federal judge, blah blah blah. You can read the whole text, and here is the summarization. The Justice Department's recommendation comes after a federal judge ruled in August that Google has violated U.S. antitrust law with its search business. So since we truncate the length to a maximum of 30 words, so it doesn't finish. I think it's pretty good as for summarization. Now the next demo I want to show is using BART to do sentiment analysis. So this is a type of sequence classification task. So we load our tokenizer and model BART for sequence classification. And then we input a task. So the task I chose is from IMDb, is a movie reviews. So for the movie called Joker, we have a bunch of user reviews. So I just pick that one. It's 3-star out of 10. It's pretty negative, I think. So let's see if our model can classify that. So this is the review, and then we put them into the model, and we get this prediction. Oh, it says the prediction is negative. And then let's try another review. So that one is an A-star review, also by the user. So let's try it again. Yeah, as you can see, the model correctly predict that this review is positive. So I think that's all for the demo. And here's the references. And thank you guys for watching.